Ostrover from Tel Aviv University in Israel. Professor Ostrover received his PhD from Tel Aviv in 2007, and after spending some time at MIT and Institute for Advanced Studies in Princeton, he's now back at Tel Aviv. Among his many prizes and honors, he received the Alon Fellowship in 2010, which is the national award to the most outstanding new Israeli faculty members in the natural exact sciences. So the title of his talk today is slightly different from what is announced, so it will be From Symplectic Measurements to Model Conjecture via Billiard Dynamics.
Thank you very much for this kind introduction. I also would like to thank the organizers for the opportunity to speak here. It's a great honor and pleasure. I'm going to talk about a recent joint work with Shiri Augsten-Mon from Tel Aviv University and Roman Karsev from the Moscow Institute of Physics and Technology. And basically, what I would like to do in this talk is to explain the relations between the three objects that... It's not working. Is it better now? I would like to explain the relations between the three objects that appear in the title. So the first one, from symplectic geometry, symplectic measurements or symplectic capacities. These are just different ways to measure the symplectic size of sets. The second object from a completely different field, from convex geometry, it's the Muller conjecture. 70 years old open question regarding the volume product of a convex body. And finally, the mathematical billiard, or more precisely, the theory of Finsler billiard dynamics. So that's the plan for the talk. And let me start with a few words about symplectic geometry. Roughly speaking, symplectic geometry is the geometry underlying Hamiltonian dynamics. So symplectic manifold is a smooth manifold equipped with a two-form omega, which should be closed and non-degenerate. And symplectic manifolds appear very naturally as phase spaces in Hamiltonian dynamical systems. There are many physical models, starting from celestial mechanics or motion of the particle in a magnetic field, that can be described using this setting, using this language. And it is classically known that the motion in those systems, the flow, preserves the symplectic structure. So in this sense, symplectic manifolds are the natural symplectic setting to study Hamiltonian dynamics. But there are some bad news about symplectic manifolds. This is kind of in a sharp contrast with Riemannian manifolds. There are no local invariants in symplectic geometry. So other than the dimension, every two symplectic manifolds locally looks the same. And these facts, the fact that one cannot perform local measurements in symplectic geometry, caused almost a complete stagnation in the field of symplectic geometry till the mid-80s. And then started what I would like to call the symplectic revolution. It started with work by Gromov and then followed by works of many other people. And what Gromov did, he developed a new theory, the theory of pseudo-holomorphic curves, and used it, among many other things, to establish the existence of global invariants in symplectic geometry. And in particular, he proved the following remarkable theorem. You can see it here on the left-hand side. It's called the non-squeezing results. And this theorem states that if you take a ball, a two-dimensional ball, and you try to squeeze it into an infinite cylinder, then the only way that this is possible is if and only if the radius of the ball is already less than or equal to the radius of the cylinder. So in contrast with the volume-preserving category, where you can, of course, squeeze arbitrarily large balls into tiny cylinders, in the symplectic setting, there are certain obstructions which prevent such embeddings. And one can use these obstructions to define global invariance in symplectic geometry. So let me be a little bit more precise. To keep the presentation simple, I'm going to focus on one symplectic manifold, the classical phase space R2n, with q coordinates for position and p coordinates for momentum, equipped with the standard symplectic structure given locally by dp dq. Now, the notion of symplectic capacity is due to Ekeland-Hofer, and this is a map which is supposed to measure the symplectic size of a set. So it assigns to a set in the phase space a non-negative number, such that it is monotone with respect to inclusion. That's the first requirement. Second, it is a symplectic invariant, and also should respect the scaling of the symplectic form. That's the second assumption. And the third assumption, which is the most important one, is that the ball, the two n-dimensional ball, and the cylinder should have the same size. Now, this is a manifestation of the non-squeezing result. And note that the third property immediately disqualifies any volume-related invariance, because of course the cylinder has an infinite volume. So a priori it is completely unclear that symplectic capacities exist. But here is an example. So given a set, we can measure what is the largest possible ball that we can symplectically embed inside the set. It's called the Gromov width of the set. And the fact that this is a capacity follows from the non-squeezing result. It's easy to check. And in fact, it is not hard to check that the existence of any symplectic capacity is actually equivalent to the non-squeezing result. So this is one example, but nowadays there are many other examples. So there are embedding type capacities like the Gromov width. There are capacities which are closely related to Hamiltonian dynamics and the question of existence of periodic orbits in Hamiltonian dynamics, like the Hofer-Zener capacity. Recently, Hutchings constructed capacities using the theory of embedded contact homology, and there are many other examples, and all these capacities play a central role in symplectic topology, and they have vast applications both in the field of symplectic geometry and in Hamiltonian dynamics. But there are some more bad news. All these capacities are notoriously difficult to compute, and in fact, there are only very few examples where we can actually compute these numbers, these invariants. And even to efficiently estimate symplectic capacities turned out to be a very difficult task. And I would like to focus on one question, one conjecture, which is due to Viterbo from 1991. Viterbo compared the symplectic way of measuring the size of sets using capacities with the classical Riemannian way using volume. And among many beautiful results, he conjectured the following thing. So, given a convex body in the phase space, then for any symplectic capacity, one has the following inequality. Here, B stands for Euclidean ball, and the power 1 over n on the right-hand side is because of dimension reasons. So what is written here, in other words, that among all convex domains in the phase space with a given volume, the Euclidean ball should have the maximal symplectic size. So if you like, this is a symplectic version of the isoperimetric inequality. This is the conjecture. And in the same paper, Viterbo actually proved this conjecture up to a constant which depends linearly on the dimension. And a few years ago, together with Shiri Avidan and Vitali Milman, we used tools from the field of asymptotic geometric analysis, in particular a very powerful tool called the reverse Brun-Minkowski inequality. And after adjusting these tools to the symplectic setting, we managed to prove that this conjecture holds asymptotically in the dimension. So in other words, there exists a universal constant, a dimension-independent constant, such that the above inequality holds up to this constant. So asymptotically it holds, but again, the original question, or the question whether this constant equals 1, is still open. So this is Viterbo's original conjecture. So what I would like to do now, I want to change gears completely and move to a completely different field, convex geometry. But before doing that, I need one more simple fact from symplectic geometry, which will be useful for us in a second. And this is the following fact: it's just linear symplectic geometry. If you have an n-dimensional space and you look at the configuration V times V star is the dual space, then this configuration has a natural symplectic structure, given explicitly by the following formula. And since it has a natural symplectic structure, it has also a natural notion of volume by taking the nth power of the symplectic form. So this simple fact will be useful for us in a second. And now let's move to Mahler conjecture. So we start with a normed space. We can assume that this is a finite dimensional normed space X. And we associate with this space a certain invariant, mu of X, in the following way. So we consider the dual space, X star, equipped with the dual norm. And then we look at the configuration X times X star, and we take the unit ball of X times the unit ball of the dual space. And we compute the volume of this configuration. This is called the Mahler volume. More geometrically speaking, it measures the volume of a centrally symmetric convex body times the volume of the polar body, or the dual body. And here I'm using the natural identification between normed spaces and convex domains, centrally symmetric convex domains, where the convex domain is just the unit ball of the corresponding normed space. Okay, so it will be useful for us to switch from normed spaces to convex bodies, essentially the same thing. So Mahler volume is an affine invariant. It is independent on your choice of base for your space X. And in some sense, you have certain intuition, it captures the roundness of a convex body, of a centrally symmetric convex body. So to support this intuition, let me state the following classical inequality, the Blaschke-Santalot inequality, which states that mu of X is maximized by, and in fact only by, Euclidean spaces. So the upper bound for mu of X is just Euclidean spaces, is obtained by Euclidean spaces. And this result can be proved using, for example, Steiner symmetrizations, which takes a convex body and makes it rounder and rounder without decreasing the Mahler volume. So this is standard technique in the field of convex geometry. This is the way one can prove the Blaschke-Santalot inequality. On the other hand, Mahler conjecture is about the lower bound of this quantity, mu of X. More precisely, the conjecture states the following: if X is an n-dimensional normed space, then mu of X is always greater than or equal to 4 to the n over n factorial. And this number is obtained, for example, for the L-infinity space, or the L1 space. This is the picture you see here on the right-hand side, the product of the volume of a cube times its dual body, the cross polytope. So as the ball is the roundest possible convex body, the cube or the cross polytopes are the pointiest possible symmetric convex body. This is Mahler's conjecture. And Mahler proved this statement in 1939 in dimension 2, but starting from dimension 3, this is an open question. And perhaps part of the reasons why this question is so difficult, even though many people worked on this question, is that in contrast with the upper bound, in contrast with the Blaschke-Santel law inequality, for the lower bound, there are other extremizers. So other than the cube and the cross polytopes, there are other convex bodies, a family of convex bodies, with the same Mahler volume. So in some sense, it's very difficult to imagine an optimization process, an optimization procedure that will converge exactly to this family of convex bodies. So this is probably part of the reason why this is such a difficult conjecture. But still, there are many partial results. This conjecture has a very long history, and I'm afraid that I don't have enough time to do justice to the history of the subject, so I will just mention briefly that Bourgain and Millman proved an asymptotic version of this conjecture. So Mahler's conjecture holds up to a constant, which is independent on the dimension. And as far as I know, the currently best known constant is due to Greg Kuperberg. So that's Mahler's conjecture. So to summarize, we have two conjectures, one from symplectic geometry, Viterbo's conjecture, which states that among all convex bodies in the phase space with a given volume, the ball has the maximal symplectic size. And after plugging in the volume of the ball and the capacity of the ball, this is exactly this inequality here. And we have the Mahler conjecture from convex geometry about the lower bound for the Mahler volume or the volume product of a convex body. And what we discovered recently is that these two seemingly very different conjectures are actually very closely related. And this is the main result I would like to show today. It is a joint work with Shiri Arshen-Avidan and Roman Karasev. And the statement is that Mahler's conjecture is actually equivalent to a special case of Viterbo's conjecture. And by a special case, I mean for a specific symplectic capacity, which I will define in a second, and not for arbitrary convex domains, but for convex domains of this particular form, a convex body times its dual body, its polar body. Now, at first, this theorem might look a little bit strange because of the extremal cases of the two conjectures. So if you recall from before, the extremal case of Viterbo's conjecture is the two n-dimensional Euclidean ball, while an extremal case for the Mahler volume is this product of a cube and a cross polytope. So n-dimensional cube and an n-dimensional cross polytope. And these two convex bodies look very much different. But on the other hand, if you put on your symplectic glasses, then it turns out that these two convex bodies are essentially the same. So roughly speaking, the product of a cube and cross polytope, again, symplectically speaking, is in fact a Euclidean ball. So I don't want to be very precise about this statement, but the idea is that there exists a symplectomorphism, a nonlinear symplectomorphism, which takes an epsilon neighborhood of the product of these two bodies to an epsilon neighborhood of the ball. So from the symplectic point of view, there is no contradiction. These two extremal cases are essentially the same. So what is the main idea behind the proof? The main idea is that there exists a capacity, a specific symplectic capacity, which I will define in a second, such that, remember from the beginning, I started by saying that in general we don't know to compute symplectic capacity, so this is kind of the first time that we have tools to at least compute this capacity for a specific family of convex bodies. So this capacity, for every such configuration, every time we plug in a convex domain, a centrally symmetric convex domain times its dual body, its polar body, equals 4. And it's easy to see that if we plug this number 4 here in the left-hand side of Viterbo's conjecture, we immediately get the lower bound in Mahler's conjecture. So this is the main idea behind the proof, and this capacity is closely related to Finsler-Billiard dynamics. This is what I would like you to do in the rest of my talks, to explain first what is this capacity, its relation to Billiard dynamics, and why for such configurations it's always equal 4. So I will need some preparation, going back to this setting of the phase space. And suppose we have a smooth compact hypersurface gamma inside the phase space, and it can be convenient to think about gamma as an energy surface of a certain Hamiltonian function, to have a more dynamical Hamiltonian dynamics interpretation. So for each and every such hypersurface, we can associate a canonical line bundle by taking the kernel of the symplectic form restricted to gamma. And if we look at the integral curves of this line bundle, we get characteristic foliation. So there is a natural dynamics associated with the hypersurface gamma. And for example, if you start, this is probably the simplest case, if you start with a sphere as a hypersurface in R2n, it's not hard to check that the corresponding dynamic is just a Hopf vibration. Try to visualize in the following picture. From the Hamiltonian dynamics point of view, what we are having here is just solutions of the classical Hamilton's equation. So this flow, this characteristic foliation, are just solution of Hamilton's equation in this given energy surface. Okay, and we can also associate with gamma certain numerical data, the action spectrum, in the following way. We take a primitive of the symplectic form, and we integrate this primitive along closed characteristics on gamma. So what we are doing geometrically, for every closed characteristic, we measure the symplectic area of the disk which is bound by this characteristic. And of course, the action spectrum can be empty. It's a very interesting and deep question in symplectic geometry or Hamiltonian dynamics, exactly when there are closed characteristics, and if there are, how many of them, and what type, elliptic, hyperbolic, and so on and so forth. But for the purpose of this talk, since we are interested only in convex hypersurfaces, and by convex I mean boundaries of convex bodies, there is a classical result by Rabinovitz and Weinstein that states that for a convex hypersurface, there exists always at least one closed characteristic. So in our setting, the action spectrum is never going to be empty. And moreover, we have the following theorem by Ekeland-Hofer and Sender, which states that for a smooth convex body in the classical phase space, the minimal element in the action spectrum of its boundary is a symplectic capacity. Now I'm cheating a little bit here because this theorem is only for convex sets, but the truth is that there exist two different capacities, the Ekeland-Hofer capacity and the Hofer-Sender capacity. Both of them define for much larger classes of sets, but in the convex case, they both coincide and are given by exactly this number, the minimal element in the action spectrum. Okay, so what is the relation of all this with Billiard dynamics? Well, there is kind of an idea, folklore idea, that Billiard dynamics can be treated as a limiting case of geodesic flow. So you can imagine that you have a two-dimensional billiard table, and then by thickening a little bit the table, you obtain a three-dimensional object, which is obtained by pasting together two copies of your billiard table and kind of smoothing the boundary. And the original billiard orbits, the billiard dynamics in the two-dimensional object, can be considered as geodesic flow on the boundary of this three-dimensional object. So this is kind of an ideology, But what is a precise mathematical statement is the following relation. So it is well known, of course, that geodesics are in one-to-one correspondence with closed characteristics in the unit cotangent bundle. And if this ideology can be made precise, then one can study Billiard dynamics from this point of view of closed characteristics. But there is a technical problem here, because what we would like to do, we would like to have this theorem, the Ekeland-Hofer center capacity, in this context. And if you try to do it, you see that you have to work with characteristic foliations on singular hypersurfaces. This is really a difficulty, because if you look at the definition above, it makes sense only for smooth hypersurfaces. But I'm not going to say anything about this, but let me just say that at least when the hypersurface is convex, these difficulties can be resolved. And what we have, well, let me just show you the picture. So what you see here is the configuration of the product of two convex bodies and dimensional convex body, K, which both of them are assumed to be smooth, K in the RnQ space and T in the RnP space. So this is a configuration in the phase space. And we want to understand the dynamics on the boundary of this product, the Hamiltonian dynamics on the boundary of this product. Now you can write down the Hamiltonian vector field, but of course at the singular strata, the Hamiltonian vector field is not defined, the product of the two boundaries. But still, one can understand how the Hamiltonian dynamics, how the characteristic foliation looks like in this example. So suppose we start at a certain point, Q1 and P1, and let's assume that P1 lies on the boundary of T, and, well, this is not what I meant in this picture, but let's assume that Q1 actually lies in the interior of the body K and not on the boundary. In this case, the Hamiltonian vector field is well defined, and hence, if we follow the Hamiltonian dynamics, what we see is that the point Q1 starts to move in a direction which is exactly the outer normal at the point P1. This is how the Hamiltonian vector field looks like. And it moves till it hits the boundary at the second point, point Q2. Now the dynamics changed, and again, following the Hamiltonian vector field, the point P1 now starts to move in a direction which is exactly the inner normal at the point Q2. So in the picture, minus the vector W2. Again, till it hits the boundary. And so on and so forth. At this point, we look at the outer normal at P2, the vector V2, and Q2 starts to move in this direction, and so on. P2 starts to move, and so on and so forth. So this is the characteristic foliation, this is the dynamical system that we get when we look at Lagrangian product of two convex bodies in the phase space. And it is not hard to check that when T is a Euclidean ball, if we take the convex body T to be Euclidean ball, and we look at the dynamics here in K, we see exactly Billiard dynamics. So the angle of incidence equals exactly the angle of reflection. And for general, let's say, symmetric convex bodies T, what we are having still Billiard dynamics, but with respect to a different geometry. So it's a Finsler Billiard dynamic. Instead of playing with respect to Euclidean geometry, we are playing Billiard with respect to the geometry which is induced from the body T. So this is the relation to billiards. And what we can prove is the following two statements. So first, if we start with two convex bodies, K and T, then the Ekeland-Hofer center capacity, which I mentioned before, the minimal action the minimal element, in the action spectrum, is exactly the length of the shortest periodic billiard trajectory in K. So we can imagine that K plays the role of the billiard table and T plays the role of the geometry. And since everything is measured with respect to the geometry induced by the body T, then the length that we need to take is not Euclidean length, but again, the corresponding length to, that comes from the geometry induced by the body T. So this is the relation between, so this is an interpretation, if you like, of the Ekeland-Hofer center capacity for such Lagrangian products of convex domains in the phase space. This is the first result. And the second result is that if you take two centrally symmetric convex bodies, K and T, and we look at this quantity, the Ekeland-Hofer center capacity of K times T, then it is given precisely by this formula. So we have now a way, at least for this capacity, this specific capacity, to compute it precisely for convex domains of this form. And what we actually have from the geometric point of view is that the shortest billiard trajectory in this case is a two bouncing trajectory that you can see here in this picture. And of course, the difficulty behind the second theorem, it is relatively easy to find this two bouncing trajectory, but the difficult part is to show that there are no shorter trajectories. So a priori, there might be somewhere here or here a much shorter trajectory. But this is not the case for centrally symmetric domains. The shortest trajectory is always this two bouncing trajectory. And you can explicitly compute the length of this trajectory, again, induced by the second body. And in the very specific situation where you take, instead of two general convex bodies, K and T, you take a centrally symmetric convex body K and T to be the polar body, the dual body. So the configuration that appears in Mahler's conjecture. Then, according to this formula, you exactly have the number 4. So this is exactly what we needed for Mahler's conjecture. In the case of playing billiard in a convex domain, in a smooth convex domain K, essentially with respect to the geometry induced by the dual body, the shortest trajectory is this two bouncing trajectory. And since we are measuring distances with respect, in a way, with respect to the same body, it's easy to check, like in the Euclidean case, that the length of this trajectory is exactly 4, right? And we're going back and forth. So this is the number 4. And this is exactly what we need for the Mahler conjecture, or for the relation between Viterbo-Bose conjecture and Mahler's conjecture. How much time do I have? 7 minutes? Okay, so let me show you some more applications of this to classical billiard dynamics. So let's assume that we are having a smooth convex body, and let us denote by alpha of k, the length of the shortest periodic billiard trajectory. So now everything is back. Euclidean billiard is the classical setting of billiard dynamics. And this quantity is kind of a very natural geometric quantity, just the length of the shortest billiard trajectory. So if you are used to Riemannian geometry, this is some analog of the systole, the length of the shortest geodesic analog with Riemannian geometry. So we can use this relation between capacities and billiard dynamics to prove the following theorem about this quantity. So first, it turns out that this quantity is monotone with respect to inclusion. So if you have one billiard table, convex billiard table, inside another convex billiard table, and you look at the shortest possible orbits, then the length is monotone with respect to inclusion. And it's somehow surprising that we don't have a direct geometric proof for this statement. The only way we know how to prove this statement is via the relation with symplectic capacities. If you remember, the first property of symplectic capacity is that it should be monotone. I will explain the relation with capacity again in a second. Another result that we have is an isoparametric type inequality. We can compare the length of the shortest periodic billiard trajectory with the volume of the table up to a constant, a universal constant, which we don't know to compute, but this estimate is asymptotically sharp. I mean, you cannot improve the square root of n that appears here. So we don't know the constant, but this is the right order of magnitude. You cannot improve the order of magnitude. Another result, again, which follows from the relations between the Ekeland-Hofer center capacity and the length of the shortest billiard trajectory, is the Brun-Minkowski type inequality. If you have two billiard tables, K1 and K2, you can look at the sum of these two tables, the Minkowski sum, an element from here plus an element from here, from K1 to K2. Then there is the following Brun-Minkowski inequality. The shortest orbit of the sum is greater than or equal the sum of the shortest orbits. And also we can prove relation between alpha of k and the in radius of the table. I should say that the inequality on the left-hand side was already known by Gomi, and on the right-hand side it's a new result. And again, all these estimates follow from the fact that alpha of k is a symplectic capacity. It's the symplectic capacity, it's the Ekeland-Hofer center capacity of the configuration k times p. So we are playing billiard in k with respect to the standard Euclidean geometry. So I think that this is probably a good place to stop. So thank you very much for your attention.
Other questions?
Could you explain more about the relation to Banach space theory? To relation to Banach space theory?
Well, there are, okay, thank you for this question. So the relation to Banach space geometry is via this interpretation of the billiard dynamics, the characteristic foliation of k times t as billiard dynamics, but with respect not to the standard Euclidean geometry, but to the Banach geometry, which is induced from the convex body T. I'm not sure if I can go back to the geometric picture from before. Right. So you see, we have essentially this picture imitates the unit cotangent bundle. We have in the configuration space our billiard table, but the geometry now is geometry which comes from a normed space. From the normed space which is associated, the unit ball is this convex body T. So it's, in a way, it's kind of a way to generalize Riemannian, the classical billiard dynamics, Euclidean billiard dynamics, to the Banach case, to Minkowski, if you like, billiard dynamics, or Finslow billiard dynamics.
Is there any relation to major concentration phenomena?
That's a very interesting question in general, whether these, say, symplectic capacities. Well, the simple answer is that we don't know, but I should say that it's very interesting if we could find some analog of the concentration phenomena that we have for volume in the context of convex domains in the symplectic setting. Of course, symplectic measurements by nature are two-dimensional. The symplectic form is a two-form, so I'm not sure how easy it would be to find this analog. Thank you.
More questions? So, I mean, which conjecture is supposed to be more difficult to improve this equivalence?
Oh, yes. So, okay, let me go back. Okay, so it can be either, so my personal opinion is the following. It can be either good news for convex people, for people in convex geometry, or bad news for, no, the other way around. Yes, no. Either good news for convex people or bad news for symplectic people. So the Mother conjecture is open for more than 75 years. But I should say that for us, this relation is very interesting because now we can try to use tools, say, from symplectic geometry to attack Mahler's conjecture, but also the other way around. So if we would like to prove this specific case of Peter-Voss conjecture or some specific cases of Peter-Voss conjecture, we can use ideas from convex geometry or asymptotic geometric analysis.
So if there are no more questions, let's thank Professor Ostrover for working.